Okay, let's dive into this. Welcome to this explainer, where we are going to unpack one of the absolutely most awe-inspiring and, let's be honest, terrifying forces of nature on our planet. Today, we're looking at the raw, unfiltered power of supercell thunderstorms, and we're going to map out the exact atmospheric physics of how a tornado comes to life. If you've ever stared up at a dark, bruised sky and wondered about the incredible energies swirling above you, well, you're in the right place. We're going to break down the science step by step and visualize the invisible forces that shape our atmosphere. It's a question that has captivated meteorologists and storm chasers for literally decades. How do tornadoes form? When you really think about this question, you have to realize we're talking about an event where the sky literally reaches down and violently interacts with the earth. Understanding how tornadoes work means looking past all the chaos of the wind and the rain. We got to strip away the noise and look at the precise, almost clockwork-like mechanics happening miles above our heads. So let's start at the very beginning, the massive engines that drive the whole phenomenon.
Section 1. Anatomy of a supercell. Building the storm.
Before we can get a twister on the ground, we have to build the right kind of storm, and that is the supercell. Supercell thunderstorms aren't just your average summer rain showers. No, these are highly organized, immensely powerful, rotating storm systems. When you look at footage of a supercell, you're seeing these towering, dark, anvil-shaped clouds just dominating the horizon. They're illuminated by intense, strobe-like lightning and driven by fierce winds. They're essentially massive atmospheric engines, sucking in energy from the environment around them. To really grasp tornado science, you absolutely have to understand the supercell, because without this rotating beast of a storm, a tornado simply can't exist.
Section 2. The atmospheric recipe. Fuel for the storm.
Now, what's really interesting about this is the combustible ingredients required for these storms to form. Every storm needs fuel, right? And here we have the ultimate clash of the titans in our atmosphere. On one side, you've got warm, moist air sitting right down near the surface of the Earth. This acts as the high-octane fuel for the storm. On the other side, moving high above it at altitude, you have a layer of cooler, drier air. Nature really doesn't like it when these two extremes are separated like this. The warm air wants to rise up because it's lighter, and the cold air wants to sink because it's heavier. When these two distinct air masses forcefully collide, the result is incredibly dramatic. That collision creates what scientists call atmospheric instability. It's a highly volatile condition. Think of it kind of like a boiling pot of water with a tight lid on it. You have rising warm air aggressively pushing upward and sinking cool air pushing downward. The atmosphere is just churning, bubbling, and fighting with itself. This instability is the foundational ingredient in our recipe. It sets the stage, providing the raw upward energy necessary to build a towering supercell. But here's the catch. Instability alone just gives us an updraft. It doesn't give us the spin. For that, we need another absolutely crucial ingredient.
Section 3. Wind shear explained. The invisible force.
Wind shear is the invisible force that takes all that bubbling instability and twists it into something far more dangerous. By definition, wind shear happens when winds change speed and direction as you move higher up in altitude. Imagine the wind at the surface is blowing gently from the southeast, but a mile up, the wind is screaming from the west at highway speeds. This difference in speed and direction creates a rolling effect in the atmosphere. It literally generates invisible, horizontally spinning tubes of air rolling parallel to the ground, like a giant invisible rolling pin.
Section 4. Birth of a mesocyclone. Creating the spin.
Let's see how this builds, because a horizontal tube of rolling air isn't a tornado yet. We need to turn it upright, and this is where the physics get truly fascinating. Step 1. We have our horizontal spinning air created by the wind shear we just talked about. Step 2, remember that atmospheric instability? It creates a massive, powerful updraft of rising warm air. This updraft rushes upward and actually intercepts our horizontal spinning tube of air. Step 3, the shear force of this rising air catches the horizontal roll and tilts it violently into a vertical position. We've now taken a rolling pin of air and stood it straight up on its end, right in the middle of the storm. This vertically tilted, rotating column of air has a scientific name. It's called a mesocyclone. It's a deep, continuously rotating updraft housed deep inside the belly of the supercell thunderstorm. You can think of the mesocyclone as the beating heart of the storm. It can be miles wide, churning and drawing in more and more air, which just intensifies the rotation. When meteorologists look at weather radar, this is exactly what they're searching for, the telltale signature of a rotating mesocyclone, because this is the incubator for a tornado.
Section 5. Tornado Touchdown. Weaponizing the Storm. The storm is now fully weaponized. What happens next is a rapid and violent escalation. From the base of that massive rotating mesocyclone, a much narrower, tightly wound funnel cloud begins to descend. The rotation is tightening, spinning faster and faster, very much like an ice skater pulling their arms in to spin quicker. The funnel drops out of the dark cloud base, stretching down toward the Earth, and then the critical moment. It reaches the ground surface. The moment it makes contact, the intense, violent rotation begins lifting dirt, leaves, and eventually heavy debris, swirling it all around the base of the vortex.
And that is the exact scientific definition of our subject today. A tornado is a violently rotating column of air that's in contact with both the surface of the Earth and a cumulonimbus cloud, in this case, our supercell. It's not officially a tornado until it reaches the surface. Everything we just looked at, the clash of warm and cold air, the instability, the wind shear, the tilting of the updraft, and the mesocyclone, was all just a prerequisite to this singular, destructive moment when the vortex finally scours the open landscape.
Section 6. The unsolved scientific mystery, the grand question.
Now you might be thinking we have this whole process completely figured out. But science is rarely that simple. Here's an incredible fact that keeps meteorologists up at night. The grand question: why do most supercells fail to produce tornadoes? You can have a day where all the ingredients are perfectly in place. You've got massive instability, incredible wind shear, and radar maps showing huge rotating mesocyclones in multiple supercells. Yet statistically, only a very small fraction of these supercell thunderstorms, roughly 20% or less, will actually go on to produce a tornado. The vast majority of them will churn in the sky, drop some hail and rain, and then simply fall apart without ever putting a funnel on the ground.
So what does this all mean? What is the exact trigger that turns a rotating storm into a violent twister? Is it a sudden downdraft of cold air wrapping around the back of the storm? Is it some micro-scale shift in friction near the ground? The truth is, while we understand the macro-atmospheric recipe perfectly, the final spark that ignites the vortex remains one of the most elusive mysteries in all of atmospheric science. Nature still holds some of her most violent secrets very closely in the dark clouds above. What do you think is the missing link? Thanks for joining me in this explainer, and keep looking up.